Hello everyone, in this video I am just going to generate pulses of certain predefined frequency by configuring the timer in output compare mode of STM32F4 series microcontroller. Let's get started. Now as the first step I am just going to open the Keil Microvision 5 IDE. So as soon as you open this IDE, you just want to create your own project for your microcontroller that you want to work on. So just click on this project tab and then click on new microvision project. And further move to the folder where you want to store your project files and then give a name for your project. So I'm just giving a certain name. I have already moved to the folder where I want to store my project files and then click on save button in this window. And in the next particular tab right over here, you just want to select the microcontroller device that you want to work on. So just type in the microcontroller device name right over here in the search bar so that you will get the particular microcontroller. So in my case, I'm just typing STM32F446RE and you can see here I'm getting the device required for my project. Just click on the device and then click on OK. And in the next manage runtime environment tab, just click on this Kinsys plus icon and then click on this checkbox core. And further, just click on the plus near the device tab right over here and then click on the startup checkbox. So when you enable these two checkboxes, that is the core in the Kinsys and startup in the device, what happens here is this Keil Microvision IDE will automatically generate the required Kinsys core files as well as the startup files required for initializing the device that you have selected in the previous tab. So our device is STM32F446RE. So for that particular microcontroller, the startup files required for initializing the microcontroller and the Kinsys core files required for running the microcontroller will be enabled in this particular project that you are creating. So click on OK. That's it, the project has been created. You can see the Kinsys file has been generated as well as the startup file has been generated for the current project, that is for the microcontroller STM32F446RE in this current project. So now we just want to create our main file and I want to write down the program from scratch in our project. So just right click on the source group and click on add new item. Here just click on .c file and then give a name for the file to be main. You can see the main.c file has been created. Now I am just want to include the header required for the microcontroller. So I am just writing as include of STM32F446XX.h. So this is the required header that we want to add or include for this particular project, since we are going to use the microcontroller STM32F446RE. And further I am just writing down my main function. So int main of return of 0. You can see this is the main function that we are going to use in our entire project. So whatever the program it may be, it starts in the main function and it will end in the main function. This is the basic rule in the embedded program. And further inside this main function, I am just writing down my infinite loop, that is while of 1. So if you are writing an embedded program, there are two basic things, that is one is the main function and another one is the infinite loop inside the main function. So before the infinite loop, in the main function, whatever the programming statements that you write are called as configuration or initialization statements, which will be executed only once in the lifetime of the program. But when it enters into the while of one or the infinite loop, it will never come out of this loop and it will always keep on revolving around in this endless loop. So this particular portion of the program is called the repeatedly executed set of statements or the logical statements of the program. So before the while of one, it is called initialization or configuration lines of the program, and inside the while of one, it is logical statements or repeatedly executed statements of the program. So this is the basic main function that we are going to use for writing down our embedded program for STM32F4 series microcontroller. So let's start up with the configuration lines of the program. Now we are just going to configure the timer of STM32F4 series microcontroller in output compare mode. So I am just opening the Nucleo user manual, and you can see this is the Nucleo development board that we are going to use, that is Nucleo F446RE, which is having STM32F446RE microcontroller mounted on it. So in this particular Nucleo development board, you can clearly see we are having a LD2 green LED right over here. So we are just going to use this particular LD2 LED in this Nucleo development board for visualizing this particular output in the hardware. So let's just find out to which pin of the microcontroller this particular LD2 is connected. So that is already available in this particular Nucleo user manual. So I'm just moving to the respective page. So you can see in this page number 23 of this Nucleo user manual, this user LD2, that is green LED LD2, is connected to PA5 of the microcontroller. So let's just configure the PA5 in output compare mode for visualizing the output in the hardware. So PA5 we are just going to configure in output compare mode of timer. Okay, this is the particular initialization or configuration that we are going to do. And I am just opening the data sheet for further understanding which channel of the timer is connected to PA5. So I am just going to open the alternate function tab of the dataset. So whatever may be the alternate functionality of any pin of the microcontroller, you can check in this particular alternate function table. So now I am just going to move to the PA5 pin. You can clearly see here is the PA5 pin, and you can see there are several alternate functionalities that is available for this particular PA5. One is the timer 2 channel 1 or timer 2 ETR, timer 8 channel 1N, SPI clock, OTG HS. So these are the 4 alternate functionalities. Other than this particular PA5 can be configured as general purpose input output pin. It can be an input pin or it can be an output pin. That can be also done other than this particular functionalities. So let's choose the timer 2 channel 1. So for doing this, we just want to note down the alternate functionality number. So here for configuring the PA5 in timer 2 channel 1, we have to select the AF1 of the PA5. So AF1 is the particular alternate functionality number which you want to write for configuring the PA5 in timer 2 channel 1. So we just want to configure AF1 alternate functionality 1 for this particular channel for configuring it in timer to channel 1. That's it. So now I have derived several steps for configuring this particular channel in output compare mode and for generating pulses of predefined frequency using same output compare mode of timer. So these are the steps. You can clearly see these are the steps that you want to follow for configuring the timer in output compare mode and for generating pulses of predefined frequency of 1000 Hertz. Here I have set the frequency to be 1000 Hertz. If you want an alternate or any other frequency, you can do the configuration as per your user defined or predefined frequency. So let's start with this. So as the first step, we just want to enable the clock of GPIO. As we are going to configure the PA5 in timer output compare mode, we just want to enable the clock required for running the PA5. So GPIO clock needs to be turned on as the initial step. So I am just opening the user manual of the microcontroller STM32F4. So here this is the user manual. So as you mention the clock, to find out where the clock of the GPIO of the microcontroller is connected, just open the datasheet of the microcontroller. This is a shortcut that I am going to show you how you can find where the clock bit of the microcontroller is connected. Just open the microcontroller datasheet and move to the page number 16. You can see the whole block diagram of the microcontroller. Here what we want is we just want to find the clock of GPIO port A. So the clock of GPIO port A is connected to AHB1 bus. So this is what we want to find, to which bus the clock of the peripheral is connected. So our peripheral GPIO port A is connected to AHB1 bus, which is running through AHB1 bus. So now come to the user manual of the microcontroller, and in the chapter reset and clock control, go to the RCC registers. Here as I mentioned, we just want to enable or open. Here as we discussed, we just want to open the AHB1 related register. So I am just opening the AHB1 ENR for enabling the clock, as well as you just want to open the 1 RSTR for resetting the clock of the GPIO. So I am just opening 1 ENR, AHB1 ENR. So here you can see the bit number 0 of this particular register is useful for enabling the clock of GPIO. So if I write 1 to this particular bit, the IO port A clock is enabled, and if I write 0 to this particular bit, the clock will be disabled. So I am just going to do the same. I am using the pointer RCC and I am pointing to AHB1 ENR, and I am going to write 1 to 0th bit. So GPIO clock has been successfully enabled, and as the next step, I am just going to set the alternate function mode for PA5. So I am opening the the user manual, and now this time I am just going to move to the general purpose IOs chapter. In this chapter, just go to the register section and open the mode R register. Here you can see in this particular mode R register, we can do 4 different configurations for a particular channel. One is you can configure the channel in input mode, output mode, alternate function mode, and analog mode. So here we just want to configure PA5 in alternate function mode. So this register is allocated in such a way that each channel has 2 bits for configuration. So if you write 00 to both the bits, it will be configured in input mode. 01 in both the bits will configure the mode of the channel in output mode, and 10 will configure the channel in alternate function mode, and 11 in both the bits will configure the channel in analog mode. So for PA5 we just want to configure bit number 10 and 11. So 0 and 1 is useful for configuring PA0, 2 and 3 is useful for configuring PA1, 4 and 5 is for PA2, 6 and 7 is for PA3, 8 and 9 is for PA4, 10 and 11 is for PA5. So here we just want to set the bit number 11 and clear the bit number 10. So for configuring the PA5 in alternate function mode, so set the bit number 11 and clear the bit number 10. So this time I am just going to use the pointer GPIO and I am going to point to mode R. So I am just setting the bit number 11 GPIO and I am clearing the bit number 10. So alternate function mode select is also done. And as the next step, we just want to configure the PA5 for timer to channel 1. So as we discussed here, when we select the AF1 mode of the PA5, then it will be configured in timer to channel 1. This data we just collected just now before the initial configuration from the datasheet of the microcontroller. So for doing this, what we want to do is we just want to open the user manual, and this time I am just going to move to the register of the GPIO, that is the alternate function register. And in this particular register you can see every channel has 4 different bits for configuration. So each 4 bits right over here, 0 to 3 is useful for configuring PA0, 4 to 7 is useful for configuring PA1, and similarly 20 to 23 of this particular register AFRL, that is low register, is useful for configuring PA5. So as we discussed earlier itself, we just want to configure AF1 mode of PA5. So for AF1 mode we just want to write 0001 for these particular bits for configuring the particular channel in certain mode. So we want this particular configuration for PA5. So I am just going to write 0001 to all these 23 to 20 bits of this particular register. So I am just going to set the bit number 20 and declare all these 3 bits for configuring the PA5 in timer to channel 1 or in AF1 mode. So again I am using the same pointer and I am going to point to AFR of 0. So if you want to write to AFRH register, that is this particular register, you just want to use the AFR of 1. Now we are just going to write to AFRL, that is low register, so I am just using the AFR of buffer 0. I am just setting the bit number 20 and I am clearing the bits from 21 to 23. So we successfully setted the timer to channel 1 configuration for PA5, that is AF1 configuration for PA5. And as the next step, the GPIO configuration and clock configuration of the PA5 is complete. Now we are just moving to the timer configuration of the microcontroller. That is, we just want to enable the timer 2 clock. So here, for enabling the clock, as we did before for GPIO-A, we just want to find the bus to which the timer 2 peripheral is connected. So I am moving to the datasheet page number 16, that is the block diagram page. Here I am just going to move to the timer 2 right over here. So this timer 2 right over here is connected to APB1 bus. So we just want to move to APB1 ENR register in the RCC. So move to the user manual and go to the chapter RCC, reset and clock control, and in the registers tab just select the register APB1 ENR. And here you can see 0th bit is useful for enabling the timer 2 clock. As you can see here, timer 2 clock enable bit. So I am just going to set this particular bit in the program. So here I am just going to use the pointer same RCC, and I am going to point to APB1 ENR. And as the next step, we just want to select toggle on match feature when auto reload register and count register of timer matches. So this is a particular configuration in timer output compare mode. So there are several configurations also available when a timer auto reload register matches with the timer count register. So when you start the timer, the counter of the timer starts incrementing or decrementing based on the configuration that you are providing. So when the value of the timer counter reaches the preloaded auto reload register value, there must be an action taken in the output compare pin of the microcontroller, that is the timer to channel 1 of the microcontroller. So that action must be defined in this stage. So here I am just going to select the toggle on match. So whenever the timer count register matches with the auto reload register value, that is the preloaded register value, the particular timer 2 channel 1 or the output compare pin of the microcontroller must toggle its state. That is, it must become low if it was high before, and it must become high if it was low before. So this is what I want the output compare pin to do whenever this particular match happens. So for doing this configuration, move to the user manual and go to the chapter of general purpose timers and timer registers. Here in this timer registers, you just want to go to the CCMR1 capture compare mode register. So in this particular mode register, go to the bits from 4 to 6. So these 3 bits define the mode of output compare. So here if you write 0 0 0, it will freeze the timer count whenever the particular match happens, and if you write 0 0 1, it will force the pin to be high whenever the match happens, and if you write 0 1 0, it will set the mode to inactive level when the match happens between count and ARR register, auto reload register. And if you write 0 1 1, it will toggle when the timer count and auto reload register value matches. And if you write 1 0 0, it will force inactive level, force low. And if you write 1 0 1, it will force high, and so on. This is what the combinations available. So we are just going to write 0 1 1 to these bits for toggling the state of the output compare channel whenever a match happens between timer count value and preloaded auto reload register value. So I'm just going to set the bit number 5 and 4 and I'm going to clear the bit number 6. So this time I'm just going to use tim2 pointer since we are writing to timer 2 registers. So CC MR1, I'm setting bit number 4 and bit number 5, and finally I'm just going to CCMR1 sorry, here I left the number 5. So finally we have set the bit number 4 and 5 and we have successfully cleared the bit number 6 for selecting the output compare mode to be toggle on match when the preloaded auto reload register value and timer count value matches. And we have finally set the configuration of output compare to be toggle on match of timer auto reload register and timer count value. And as the next step, we just want to enable the output compare mode. So that you can find in the register CCER of timer. So you can clearly see this is timer capture compare enable register, and this particular register has many bits. Among these bits you just want to enable the bit number 0 for enabling the output compare signal. So bit number 0 must be enabled. tim2 CCER. So here, before configuring the frequency of timer, we very well know that the system is running at internal oscillator of 16 megahertz. 16 megahertz nothing but 16,000,000 hertz. So now we just want to configure the frequency of timer in such a way that it runs at 1000 hertz. So for that we are just going to use a particular register in timer 2 peripheral, that is PSC. So I'm just writing a rough value of 1 right over here in the PSC. So this PSC is nothing but prescaler register. So this prescaler register holds a value that is nothing but division factor for configuring the clock of the timer. So before configuring the clock of the timer, you just want to set this particular prescaler in such a way that the required clock configuration for the timer 2 or any timer is fulfilled. So this is nothing but a division factor for configuring the clock of the timer peripheral. So the system clock is 16 megahertz. So the required timer frequency or the configuration required for clock configuration required for timer 2 is 1000 hertz. So division factor for arriving this 1000 from 16 megahertz is nothing but 16,000, right? So I am just loading the value 16,000 to this particular PSC. Since the value starts from 0 to 15,999, I am just subtracting the value 1 from it. That's it. So this particular PSC is nothing but prescaler. I will show you that also in the user manual. PSC. You can see prescaler. The counter clock frequency is equal to frequency divided by the PSC of 16 bits. And as the next step, we successfully, and here we successfully configured the timer 2 clock to run at 1000 Hz. This is successful, and now we are just going to configure the match to exactly happen at 1 second. So we configure the timer to clock to run at 1000 Hz. So the time period of the timer 2 is nothing but 1 divided by 1000 Hz. That is the frequency of timer 2. That is nothing but 1 millisecond. One divided by 1000 Hz is nothing but 0.001 second or 1 millisecond. So for timer 2, it takes exactly 1 millisecond for every single tick. So for configuring or providing the match at 1 second exactly, we just want to load the value 1000 millisecond to the ARR register. Am I right? So the timer 2 runs in such a way that for every tick it takes exactly 1 millisecond. To achieve 1 second exactly, we just want to load the value 1000 to the ARR register, that is the auto reload register. So here I am just going to point to ARR and I am going to write 1000 minus 1 to it. It starts from 0, so 0 to 999 will give us 1000 as the exact value. So now the configuration is over. Here we have configured the timer to run at 1000 Hz, so that for every tick the timer 2 takes exactly 1 millisecond. And here in this particular line we configure in such a way that the output compare channel of the timer 2 will toggle whenever the match happens between timer count value and preloaded auto reload register value. So we want the match to happen exactly at 1 second. So we calculated the tick of timer to be 1 millisecond. So we exactly loaded the value 1000 to the preload register value, that is ARR register, in such a way that the toggle happens for every 1 second or 1000 millisecond. So we loaded the value 1000 right over here. Now what happens is the timer starts from 0 and exactly when it reaches 1000 millisecond, the timer count value matches with the ARR register value, that is 1000, and the timer output compare channel, that is timer to channel 1, toggles. And again the timer counter will be loaded with the value 0, and again when it reaches the value 1000, that is 1 second, again it toggles and it goes on like this. So exactly a pulse of time period of 2000 millisecond, that is 500 millihertz, will be generated in the timer to channel 1, that is PA5 of the microcontroller STM32F446RE. So for every 1 second, the PA5 timer to channel 1 will toggle its state, making or generating a pulse of 500 millihertz or pulse with the time period of 2000 millisecond or 2 seconds. So as the next step, I am just going to initialize the timer count value to 0. So CNT is the timer count register, and as the final step I am just going to enable the timer. So for this you just want to move to the timer control register, that is CR1. Here you can see CEN, bit number 0, counter enable. You have to point to CR1 and you want to set the bit number 0. So that's it. We have successfully configured PA5 in timer to channel 1, and we successfully configured timer 2 for generating pulse of exactly 500 millihertz using timer output compare mode of STM32F446RE. Let's just visualize the output in the hardware. I'm just building this project. Just click on the F7 in your keyboard or this particular icon right over here for building the project. You can see the build is successful with 0 errors and 1 warning. That is fine. Now click on the options for target right over here and go to the debug tab right over here and select the ST-Link debugger. Click on the settings button. You must see the ID code of IC connected. As soon as you connect the USB cable from Nucleo F446RE development board to your PC and then click on OK. OK. Now click on this particular icon or F8 in your keyboard for downloading the flash to the microcontroller. You can clearly see the flash load finished at particular time and the programming is done, verification is done and erase is also done. So now let's just visualize the output in the hardware. You can see this is the Nucleo F446RE development board which I am having, and I am just resetting the board. The flash is already dumped. So here you can see the LD2 LED in my Nucleo F446RE development board is blinking at a rate of exactly 1 second. That is, on time is 1 second and off time is 1 second, making a pulse of 500 millihertz. So the PA5 pin of the microcontroller is connected to LD2 LED right over here. So this is configured in timer 2 channel 1 of output compare mode and it is generating a pulse of 500 millihertz. So this is the output that we got in the hardware. See you in the next video. Thanks for watching.